Good morning. Uh, in today's class, we will be starting with the digital filter, and specifically, we will be concentrating on the FIR filter in this chapter. So, in our last few classes, in fact, we have been discussing about how the placement of the poles and the zeros they can affect the amplitude response, and they can also affect the phase responses of any given filter. We have also looked into how the rubber membrane concept, both in the S plane and in the Z plane, can help us understand what would be the frequency response of a filter if we know the positioning of the poles and the zeros. Okay. So now from this chapter onwards, we will be slowly diverging or ingressing into the numericals, and we will be taking up some numericals and see how to design the filters. So in the first chapter, we will be basically focusing on the FIR filters, and then in the next chapter we will be discussing about the IIR filters. Okay. Now, in many textbooks, you will find that initially they start with IIR filters and then they discuss about the FIR filter. But I do the reverse because FIR filters are easy to implement. So, since it is easy to implement, you will get a feel of how to design the FIR filters in a very easy manner. And once you are accustomed with the FIR filter designing, then we will get into the more complicated methods for the designing of the IIR filters. Okay. So, as I told you, the digital filters they are categorized into two types: FIR filter and IIR filters. Okay. So before going into this IIR filter and the FIR filter, I am just again repeating what is transfer function, which I have been discussing with you since a long time. But before getting into the details of the filter designing, let's discuss it once more so that it remains fresh in your mind. Okay. So, what is a transfer function? Transfer function xz, it is given by yz by xz. Okay. Now, in many cases, you will find that students, specifically those who are from the, in fact, who are not from the electronics and instrumentation, electronics control or computer science background, they mix it up. Okay. So, let us understand what is the transfer function. For that, let us take a simple analog circuit, non-inverting amplifier, which all of you must have studied. Okay. So, in this analog circuit, that is the non-inverting amplifier, the output voltage V0, V out, it is given by 1 plus R2 by R1 multiplied by Vi, which is basically the voltage input. Okay. Now, if you bring the Vi on the left hand side, then we get V0 by Vin, which is given by the gain A. Okay. And this gain A, it is given by 1 plus R2 by R1. Now, this R2 by R1 component, it is nothing but the transfer function of the non-inverting amplifier. Okay. Now, since in this transfer function we are having R1 and R2, so this transfer function, it is basically frequency independent transfer function, and hence it is usually represented with A. However, instead of this one, if we include some reactance components, say Xc or Xl, or a combination of both of these, then this gain, it would become dependent on the frequency of the input current, right? Or the input voltage, sorry, not current, voltage. So, what is this Xz? Xz is nothing but a function which is varying with frequency, because z plane, here when we talk about this z plane, we have this z operator, which is nothing but a complex operator wherein the frequency is related with the z. Okay, digital frequency, it is related with the z. So in other words, we can say the hz, it is dependent on the frequency component. So if you see, what is v0? V0 is the output. So that is what it has been given over here, yz, and vin is the input, and hence we are having the xz component over here. So xz is equal to yz by xz, output by input, okay, in the complex domain, right? Previously, we have also discussed that hz, it may be given by a combination of two polynomials pz by qz, okay, pz by qz. Now discuss let us discuss what are the differences in the FIR filter and the IIR filter. Okay, as the name suggests, in the first case, FIR filter, finite impulse response, finite impulse response. The acronym FIR, it is basically corresponding to the full form of finite impulse response. In our last few classes, we have already discussed what is impulse response. So if we are given with an amplitude, a LTI system, if we are given with an LTI system, so if we give say delta n as the input, the output what we will be getting is the hn. Okay, so we give xn, we get yn, which is equal to basically this xn convolution of h of n, right? So this is the basic formula of the output of a given system for a LTI system. Okay. Now in this LTI system, if we give an impulse input, that is at n equals to 0, we have an impulse, and at all other time instances we have 0 amplitude, then the output what we get is the impulse response. Okay. Now, as the name suggests, finite impulse response. Okay, what do you mean by finite impulse response? Finite means there would be a finite sequence of the hn value. A finite sequence of the hn value. That means, say, if I give delta n as the input, so for that I can get an output which is equal to, say, 1, 4, 4, say 3, something like this, and thereafter, after a certain values, you will start getting 0 components. That is, the length of hn is finite. So you can, in other words, you can say that finite sequence values. Okay, so you have finite number of the values in the as the impulse response. Okay, and hence we call it a finite impulse response filter. So all the FIR filter, they are finite impulse response filters. So they will be having a finite sequence of the impulse response. Okay, now coming to the IIR filters, What is the full form of this acronym IIR? Infinite Impulse Response. Impulse Response. So from here, what we know that if we compare the previous one, it was finite impulse response, and in the second one we will be having an infinite sequence of HN. So number will be present till infinity. Okay. However, we have previously discussed that for a system to be stable, so what is the condition? At n tending to infinity, our amplitude values, it should tend to 0. In this case, the Hn values, it should tend to zeros. Then we will be able to design a stable infinite impulse response filter. Then we will be able to design a stable infinite impulse response filter. Okay. Now the FIR filters, they are regarded as the non-recursive filters. They are regarded as the non-recursive filters, whereas IIR filters, they are regarded as the recursive filters. Okay, they are regarded as the recursive filters. So what does that mean? This means that the IIR filter, they will be having a feedback system or a feedback loop. So let us take the example of this non-inverting amplifier. If you see over here, the output of the system is taken to calculate the next output. Okay. So what happens over here? We are having Vi over here. So no current flows into the op amp. So at this position we are having Vi. So correspondingly, at the inverting terminal also we will having Vi. Considering Vi is positive in nature, in which direction the current will flow? The current will flow from Vi to ground. That means at the inverting terminal, no currents either flows into or out of the system. So from where the current is being supplied? The current is being supplied from the output region. So the current flows from V0 to ground, right? So over here what we are seeing, the output of the system, it is being taken to calculate the next input or the gain of the overall gain of the system, right? So here you can see we are taking information from the output and then we are calculating some output again. Okay, so this kind of system, they are regarded as feedback system. So feedback systems, they are very good in processing the signal components. However, we have to be very careful that the system does not get unstable in nature. Okay, so sometimes if you do not take care, so what happens is that the system may get unstable in nature. So say for example, usually any op amps, they are being operated at plus minus 12 volt. Most of the op amps. Okay, there are certain op amps which can be powered by plus minus 5 volt power supply. Some may be powered by plus minus 15 volt. But under normal laboratory circumstances, most of the op amps, they are being powered with plus minus 12 volt power supply. And when we try to operate the op amp using a plus minus 12 volt power supply, the operational range of the op amp, it is usually 2 volts lower than the supply voltage. So that means the operational region, it is within the region of plus minus 10 volts. Okay. Now since it is within the region of plus minus 10 volts, so suppose here the gain is 5. Here the gain of the system is say 5. Now if I give 3 volts, it will go and get saturated at 10 volts. Over 10 volts, it will not show any results. So that is the problem with the type of this what do you call feedback systems. If you do not take care of the system parameters, then you can get unstable readings. Okay, so you have to work within a specific what do you call a specific input region. Okay, so yeah. So apart from that, when we are talking about the IIR filters, we will later on see, we have previously discussed that all the poles, they have to be placed within the unit circle. So while designing the filters, if we design a filter with the feedback system where the pole is outside the unit circle, then the even with the same output what you give, here what I have told in the previous case, in the non-inverting amplifier case, that we are changing the input values. Okay, but in the second case, in the IIR filter, what I am telling, will be keeping the voltage same and we will be changing the placement of the poles. So what will happen? By changing the placement of the poles, we will see that the system is getting an output which is growing, okay, or it is remaining stable throughout the time. So in the next case, the system is marginally unstable. In the first case, when the output is growing out of bound, the system is basically unstable in nature. The system is basically unstable in nature. So these are the things which we keep into mind, that recursive filters, they are very good filters to work with, but we have to be super careful while designing the filters. Okay. Now the FIR filters, they have a generalized equation of this one, hz equals to summation of I equals to 0 to n hi z to the power minus I, which corresponds to h0 plus h1 z inverse plus h2 z to the power minus 2 plus hn z to the power minus n. Okay. So if you carefully look into this system, say for example, I have a system, say 1 plus 2 z inverse. Okay. If I have to calculate the poles and the zeros, what I have to do? Okay, or we can also say z. Okay, so what we get? Z plus 2 divided by z. So we have a 0 at z equals to minus 2. We have a pole at z equals to 0. Okay. Now say for example, if I have another one, take the example of this one, hz equals to 1 plus 4z inverse plus 4z to the power minus 2. So we have in this way 1 plus 2 z inverse whole square. So if you solve it like this one, 1 by z inverse and again 1 by z to the power minus 2, means if you multiply the numerator, it has been multiplied with z to the power 2 and here also z to the power 2. So what we get? We get this z it gets multiplied, one z gets multiplied with this one, and we get this equation hz equals to z plus 2 multiplied by z plus 2 divided by z square. So where are the poles? Zeros. Zeros are z equals to minus 2, again minus 2. There are two zeros at minus 2 and minus 2. And what about the poles? Poles are at z equals to 0, comma 0. Right? Now if you look into the positioning of the pole when we were having only single pole and when we have got two poles, in both the cases, where are the poles? At the origin of the z plane. At the origin of the z plane. Okay. So what is happening over here? What was our condition for designing a filter? Sorry, this is imaginary. So what was our condition? The pole should be within the unit circle. So the origin is always at the unit circle. So we can basically, from here we can generalize that FIR filters, they have poles always at the origin. And since the FIR filters, they have poles always in the origin, they are inherently stable. If you see, inherently stable. The FIR filters, they are inherently stable in nature. Okay. Are you getting my point? So this is not the case with the IR filter. In IR filters, poles, you have the flexibility to put the poles at any locations in the Z plane. Since you have the flexibility, there are chances that while designing the filter, you may do some mistake, and due to that, the poles may be placed either onto the unit circle or outside the unit circle, and in those two cases, the filters become either marginally stable or unstable in nature. Okay, but this is not the case with the FIR filters. FIR filters, they are inherently stable in nature because they always have the poles at the origin. Okay, they always have the pole at the origin. Now we also previously discussed that for the realization we need the equation in where we have the delay, because when we talk about the digital operators which are used for the designing of the filters, we have a delay. We do not have an advance. Advance means Z. Okay, we do not have the advance. However, we have the delay, and hence this equation, this generalized equation, it will be used for the realization of the filter. Okay, whereas this form of the transfer function or the equation, they will have, it will be used for computing the poles and the zero locations. Okay, pole and the zero location. Now coming to the next topic, Herein we start with hz, which is given by 1 plus 4z inverse plus 4z inverse 2. Okay. So, if I ask you realize the filter, how will you realize it? So hz, if you see, we have just discussed that hz is equal to yz by xz. So we will take xz over here, multiply it. So we get yz equals to xz plus 4z inverse xz plus 4z to the power minus 2 xz. Okay. Now this will be used for the realization of the filter. So initially we will have xz and yz. So just put the values xz and yz. Then if you see yz equals to xz. So here we have an addition. Y is an addition of various components. So our xz, it directly goes to the adder because we are having xz plus something. Now in the plus something we have z inverse. So multiplied by xz. So xz is coming. We are getting into the delay, and then there is a multiplier of this one. So we get to the point B, then we have 4 as the multiplier. This is the multiplier. Then this component is added to the xz plus the next component. So here there will be an adder. So from this adder we will be going, the output will be added to the yz. Similarly in the second year, if you see z to the minus 2, so minus 2 xz, so one z inverse has already been given, another z inverse is given, then what is the multiplier? 4. Okay, so it is being added to the previous component. See, this component is added over here. So in this whole realization of the filter, we have two adders. So see, there are two adders, 1 and 2. You consider this 1 and 2. Okay. So at this point, location D, what is happening? Xz is directly coming here, plus 4 multiplied by input is coming over here, 4 multiplied by xz, there is only one delay, plus 4 multiplied by xz. So before coming to this point, we are having two delays, minus 2. Okay. Now if you are given with the xz or the z transform, how to get into the difference equation? So difference equation is given by yn equals to xn plus 4 of x of n minus 1 plus 4 of x of n minus 2. Okay. Now if something is given in the difference equation, you should be easily able to derive the z transform. Okay. So see, if there is n minus 1, n minus 1 means there is a delay of 1. If it is n minus 2, there is a delay of 2. So you can see the correlation. So it will be very easy for you to convert from z transform to the difference equation and from the z difference equation to the z transform. Okay. So you just map this. Z inverse means you will be getting input delay by 1. If it is z to the power minus 2, it would be n minus 2. If it is say z to the power minus b, it would be x of n minus b. Okay. Now let us calculate the impulse response, then you will be able to appreciate what is impulse response. So what happens in impulse response? We have 1, and then at all other instances we are having the input of 0. So at the first instance, say we have 1. At D, what will be having? 1 plus. At B, what should be there? Previous instance, it would be 0. Previous to previous instance, it would be 0. Okay, 1 plus 0 equals to 1. So at first instance, it is 1. In the second instance, it will be 0. What it should be? At B, we should be having the previous instance value 1. Here, the previous instance value 0. Okay. So now, in the second instance at D, what we will be having? 0 plus 1. 1 multiplied by 4 plus 0. Okay. In the next instance, 0. In the previous instance, if you see, it's 0. Here, it is 1. So what we will be having? 0 plus 0 plus 1 multiplied by 4. 4 equals to 4. Then what? 0. Previous instance is 0. Here also the previous instance is 0. So everything will be 0. 0 plus 0 plus 0 equals to 0. Okay. And then as you continue, you will get 0, 0, 0, 0. So what you get? You get YZ. Since you have given the input as the impulse input, it is basically HZ. इसका सीक्वेंस अगर देखेंगे, नॉट HZ, YN let us take. YN equals to H of N equals to 1, 4, 4. Okay. So what is the HZ? 1 plus 4 Z inverse plus 4 Z to the power minus 2. What is it? It is nothing but the system what you have started with. You're getting my point? So in this way, you will be able to check whatever the filter you have realized, whether you have realized correctly or there is a mistake. Okay. There is another term which is regarded as signal flow graph. It is similar to the realized filter. In the realized filter, there is a transfer of the signal component. In the signal flow graph, we just show the direction of the flow of the signals. Okay. So it happens over here. If you see, there is these arrows, multipliers over here, which are triangular in shape. They are just being given by converted or depicted by these arrows. Okay. And then these lines, they become this curved in nature, not straight. So in this case, what we have done, we have taken the transfer function and as it is, we have implemented it. Okay. So this is called direct form of realization. There is no multiplication in between of the different subcomponents. However, we have seen few moments back, the same system, it can also be represented with this equation. H of Z equals to 1 plus 2 Z inverse whole square. So you can see we are having two subsystems, 1 and 2. Okay. So 1 plus 2 Z inverse, 1 plus 2 Z inverse, and it is multiplied. Multiplication means cascading. Okay. So This is cascading type of realization of the filters. Okay. So initially we have implemented 1 plus 2 z inverse, and here also 1 plus 2 z inverse. Okay. So at D, it should be, there is a mistake, so please correct it. So what is happening? We have different points A, B, C, D, E. We have different points. E is the output. So A is the input. 1 exact when we give 1. At A we will be having 1. At B we will be having 0. At C directly this is coming. A and B, they are basically shorted. So A and C we are having same value over here. Then next at D, what we will be having in the previous instance, here there was nothing at this delay, so it is 0. Okay, so output what we are getting directly, this 1 we are getting, because over here there are nothing. In the second instance, if you see at B when it is 0, at A when it is 0, at B we will be having 1. In the previous instance in the output we were having 1 because these are present over here. At C what we are having? At C we are having 1. So at D we will be having 1. Okay. So E what we will be having? 1 multiplied by 2. 1 multiplied by 2, 4. So Y we will be having 4. Okay. In the next instance, what we have at C, we are having we are having the value of 2. So at D, so it got and stored in the delay. So at D, we will be having the 2. 2 multiplied by 2, 4. It will be 4 over here. However, in the previous cases, directly from the input there is nothing, 0. So 4 plus 0, this thing. So you get again 4. And as you go on, no values will come out. So again, if you see, you get Hn equals to 1, 4, 4, which corresponds to the Hz of 1 plus 4z inverse plus 4z inverse minus 2. Okay. So as I told you, all the filters, FIR filters, they are LIGO stable because all the poles are within the units.
For the second instance, how the code
In the second instance, how the pole comes? What is the A?
is
A is 0. Okay. In the previous instance, what was A? 0. Second instance, this is the second instance. In the previous one, okay. So, if you have, if it is 0, what is the previous one? 1. After delay, it is released over here, so it gets multiplied by 2. 1, it came to C immediately. There was no delay. So, this one will be available at the point D in the next instance. That means the current instance 1 multiplied by 2, 4, 1 multiplied by 2, 2. So at C you have 2, at output of A you have 2, 2 plus 2, 4. Okay. So I know there will be a confusion. So both these numericals you do it now. Okay. You have seen that. You have understood this. Now you perform.
Sir, for C equals 1 what, sir?
Uh-huh.
Like C equals to 1, 0, 0, you said.
Uh,
But like at D, I had 0 in A, so that there was a delay, so 1 comes to B, right?
hmm.
And C and D also have 0, 0.
Hmm.
Done. Next, for now, when I come to C, so the 1 it goes from
See,
E to C.
first is 1,
Yes.
A is 1.
1
When
and the
it,
rest is 0.
this is previous instance 0,
0.
this is 0. Okay. So here C we have 1.
1.
E output of this one would be 0, 1. 1 is coming. Okay. A is 0. It would be released over here 1. It would be released over here 1. Okay. So at C what you will be having? 2 multiplied by 1. It will be released in the second instance. So here what we will be having? 1 multiplied by 2. So 2 plus 2, 4. In the next instance, this is 0, this is 0. These 2 has been lodged previously. So if this is 0, this would be also 0. So this 2 was lodged in the previous cycle over here. So here it comes 2. 2 multiplied by 2, 4. 2 multiplied by 2, 4 plus 0 at this point.
So irrespective of the equation, we can design in any manner, but we get the same answer.
Yes. This is called the cascading of the system, where you are having two subsystems where their outputs has been multiplied. Okay, so two subsystems are being multiplied. Okay, the equation is the same. Equation is 1 plus 4 z inverse plus 4 z inverse 2. Okay, z to the power minus 2. Yeah. So this is how it is done. So please practice it.